Now, next topic is diameter of a set. So first, what is diameter? If we have some A non-empty set in metric space XD, XD is some metric space and A is a non-empty set. So delta of A denoted as diameter of set A, which is a dpq, is the distance of any 2 point in A. So that is the distance between any 2 point in A. The supremum of numbers, that number set of numbers is called a diameter. So what do you mean by diameter? Diameter is supremum of PQ belongs to A, distance between P and Q. This is called a diameter of the set. Now, next result is, let X be a totally bounded metric space. So this is a totally bounded metric space. Then every subset Y contained in X, Y is some subset contained in X, has infinite subset A with the diameter delta of A less than epsilon, with epsilon greater than 0. So first understand the question. We have total space X. So this is total space X, that is a totally bounded. And this is second set Y, this is Y, and it has some infinite set A whose diameter is less than epsilon. Our purpose is that we want to find a infinite set A whose diameter is less than epsilon. Now from this, A is infinite, subset of Y, and Y is subset of X. What is X? X is totally bounded. Then by definition of totally bounded, it has finite epsilon net. It has finite epsilon net. That finite epsilon net is suppose x1, x2 and xn. For epsilon 1 we choose epsilon by 2, right? Then this is contained in finite ball. That balls are with center x1, x2 and xn, because these are vector in epsilon net. Now this equation 2 and this equation 1, A is part of Y, Y is part of X, and X is part of these finite union, right? It means this A goes to part of this finite union. It means A is part of this union. Clear? If A is part of this union, now A contains infinite number of elements. Remember, these are finite ball. Clear? So if we take every element of A that is part of these finite union, A contains infinite vector, and these are finite open bar. So remember this. For every P belongs to A, every P belongs to A, it belongs to this union. This union. It means P belongs to any one of the ball. So P belongs to ball with center xj, epsilon 1 for some j, right? It means distance between P and xj is less than epsilon 1, right? So correct this number. This is a xj, not pj. So this is a xj. So correct this as it is a P belongs to xj epsilon 1. So difference between these two vectors is less than epsilon 1, right? Now distance between PQ by using triangular inequality, this is TPXJ plus DXJ comma Q. So this term by using this is less than epsilon 1, and this term XJ, this XJ, this is a from this so this is again less than epsilon 1. Why? Here it is Q. This is on same line because when P belongs to A, it satisfies this condition. When Q belongs to A, then it again satisfies this condition. So this is less than epsilon 1 plus epsilon 1. So 2 epsilon 1 which is equal to epsilon. So distance between PQ less than epsilon for every PQ belongs to A. Now taking supremum, it implies diameter is less than epsilon. So that is our result. Now next result is every compact metric space is complete. That we already read it in the lower classes. So every compact metric space is complete. So let's take X is compact. Our purpose is X is complete. To prove complete, we will take some Cauchy sequence that converge to point of X. So Pn be a Cauchy sequence in X, right? Since Xn is compact, then by definition of compactness, every sequence has convergent subsequence. Then the sequence Pn has convergent subsequence. So that converge to a point P belongs to S. Then it means Pnk belongs to N. It means distance between P and K, comma P will approaches to 0, right? Since Pn is Cauchy sequence, then distance between Pm and Pn approaches to 0 as Mn approaches to infinity. Clear? Now, dPnkP is less than equal to this form, and this approaches to 0 by Cauchy sequence, this approaches to 0. So total approaches to 0. It means Pn approaches to P and P belongs to X, then X is a complete. So this is a simple result of compactness and completeness. So every compact metric space are complete. In the next lecture, we will discuss a very important article that is called spectral property of compact linear operator. Till now, we learn the compactness, compact linear operator. Now, what are the spectral property of these compact linear operator on normed space that we will discuss in the next lecture.